Right. Hello and welcome to my talk about the Eclipse Serializer project. I'm with the company MicroStream, the leader behind this open source endeavor. Eclipse Serializer is one of the successor projects of the MicroStream project. We split it up into Eclipse Serializer and Eclipse Store and moved it over to the Eclipse Foundation, and that's where the name is coming from. Just to avoid any confusion beforehand. All right, some legal stuff I have to show. And so what is serialization in the first place? Basically, object graphs or data is converted in a transport format, like a byte stream, XML, JSON, mostly, and then converted back on the receiver side. It is used to transfer data over network, or store data in caches, or copying data, for example. And the sender and receiver, of course, can be different things. They could be in the same JVM. If you put data in a cache in the same JVM, or the sender and receiver can be on different machines or on different continents, wherever the need is to serialize data to. So it's a very simple concept. Basically, you modify or you convert data into a transportable format and back, and that's what serialization is all about. So, and it is used basically everywhere. It's used in stream processing frameworks or data grids. So if you have object graphs or data, you have to serialize it into mostly bytes or JSON, and then it's processed or put into the streams pipelines and processed further on the other side by handlers. The handlers deserialize data, manipulate it, and put them back. It's used with remote method invocation, of course. It's used in application servers to store session data, for example. Of course, web frameworks running on application servers use serialization heavily. And the most common use case nowadays, I guess, is calling REST services. Mostly data is put into the JSON format and used on the server side, or objects are created on the server side out of the JSON data, and so on and so forth. Search indexes are a popular example as well, like Lucene. It's omnipresent search library, which is used in Apache Solr or Elasticsearch. And so you can see serialization is a big thing in the Java world. There are a lot of frameworks which do serialization. It's built in a JDK as well. And because there are different needs for different formats. If you want to communicate, for example, from JavaScript to Java or different languages, JSON would be the way to go. If you just want to transfer data from JVM to JVM, you will use a byte-based format because it's quicker. So depending on the use case, there are different frameworks. So, but there's a drawback. Mark Reinhold, the chief architect of the Java platform, once said the serialization was a horrible mistake, and most of the vulnerabilities are actually linked to the current serialization implementation in a JVM, and due to backward compatibility issues, they just cannot remove it or update it in a way that makes it bulletproof. And that's why a lot of frameworks are stuck with the unsecure serialization or have to switch to third-party libraries. And yeah, that's a real problem in a JVM. So Brian Götz had or said that they did a lot of conceptual mistakes back then. Now, of course, the ongoing tax is at the library maintainers and users. And like we can see here from a CVE report, you can look it up on a CVE details sites or Shodan. It's one of the CVE databases. Just put in Java serialization and you will find hundreds or thousands of vulnerabilities. And yeah, so you can see it's a real problem we have to tackle in our domain, and it's a cumbersome security leak in the JVM itself or in different other languages as well. Yeah. So the most common or most known vulnerabilities, I guess, would be one of the Apache Commons collections library. They fixed it until now, but they had an insecure deserialization of data, which may have resulted in an arbitrary code execution. So you could bring down a server um, or steal data or whatever you want to do in an application if you were able to inject the code. The struts framework vulnerability was a big thing back then. There were thousands of servers. The data here is from 3 years back, and they had still 300 open issues in a JDK regarding serialization back then. So obviously it's a huge problem you have to tackle. And the JDK implemented, or the internal JDK serialization has limitations as well beneath or besides the vulnerabilities. So you can say since all serializable classes in a class bus are serialized or deserialized automatically, it is easy to inject malicious code. You can only protect yourself by black and white listing if you know what objects are coming in. And the limitations, of course, are you have to implement a Java IO serializable interface. So if you want to serialize different classes or different objects from frameworks which are not serializable, you're not able to do so, because if you can't control the code, you cannot make your object serializable afterwards. And they don't have an API contract. It's just magic methods. They are on interfaces where you can say, I will read and write. So these are magic methods. So, and of course, after deserialization, you get an object copy. So it's hard to merge data back or objects back into a live object graph. So to keep two different object graphs synchronous is not possible automatically. So you have to do it by hand, of course. So what about the different other libraries like Jaxby, JSON, Creo, you name it, there are hundreds out there. They share the most of the drawbacks as well. Mainly we can differentiate between bytecode-based and human-readable ones. The bytecode-based ones make basically the same conceptual mistakes like the Java serialization built into the JDK. And for example, the depth of the object graph is limited because they use internal stack-based recursion. So you can run into stack errors and the JVM crashes. The human readable formats are limited by design. So they can only picture trees and not graphs, which have cyclic or circular references. The format just doesn't just can't do it. It's not suited, of course, for really huge amounts of data because it has a really big overhead, needless overhead, if you ask me, because it's focused on human readable, but most of the time only machines read it. So if you transfer data or use serialization for purely the sake of transferring data, I would prefer a bytecode-based one, except the situation needs to use human readable formats, of course. So Brian Götz tried to tackle this problem, and he wrote a paper or proposal called Towards Better Serialization. It was in 2019, and yeah, they did. He showed a design, but it still has flaws. It still breaks the referential integrity. It violates separation of concerns. You don't have external handlers, but internal ones. And it's only a draft for an API and not a concrete implementation of a serialization. And yeah, there's not much going further from there. Yeah. So, and yeah, there's always a remaining security risk when you deserialize objects from some state. And yeah, Java's implementation of serialization has been what has been called a gaping wound by Kevin Borrellion, and adds that every framework to support other wire formats has always had a start from scratch. So we had the idea to build a storage engine now called Eclipse Store, and we had to use some kind of serialization to get a persistent state of an object graph. And that's why we checked out all the existing frameworks, but all available solutions were not really sufficient back then. So we had to come up with a new way. And that's where the Eclipse Serializer project had its origins. It's basically the base for the storage engine itself. And because there are a lot of uses for serializers out there, we decided to split up the project into two parts, the Eclipse Serializer for a standalone use and the Eclipse Store built on top. It's developed newly from ground up. It's designed to eliminate the shortcomings of existing serialization frameworks, and it's optimized for security, flexibility, and of course performance. And it's used in all the modules in MicroStream before and now in Eclipse Store as a base. What did we do differently? First of all, we separate data and metadata, meaning unlike the JDK serialization, where the class information is put in the serialized state as well, we hard-coded separation of data and metadata. It's not possible, or we decided so to get the security flaws eliminated for deserialization. And the second big point is we don't execute code at the deserialization process. So injecting malicious code is technically impossible. And the referential integrity is secured through an internal mapping called Swissling. It's even on Wikipedia, it's actually a thing. It's heavily used by a storage engine as well, not only to ensure the referential integrity, but also to index the storage data for random access or direct access via hashing algorithms. So the engine assigns a long number to each object internally and uses this as the reference code to restore the graph afterwards without breaking the integrity, of course. So how does it work? On every initialization, Eclipse Serializer analyzes the current runtime's version of all the required entity and value type classes and derives an optimized metadata from it. And it's meaning it's only done once. The same is done when encountering a class at runtime that was unknown so far, so it's built on demand. The analysis is done by reflection, but since it's only done once for every handled class, the performance cost is negligible. So because we use the metadata afterwards. And the actual storing and loading or serialization and deserialization is done with an optimized framework code based on the created metadata. If a class layer changes, let's say you add a field, rename a field, change inheritance or whatever you do, the type analysis creates a mapping from the field layout that the class's instances are stored into that of the current class. It's done automatically if possible, unambiguous changes or via some configurable heuristics. Otherwise, we are user-provided mapping, so you can exactly define how a mapping should happen or type conversions should be handled. The performance for this conversion stays the same, since the JVM does not care if it, simplified speaking, copies a loaded value to address 3 or to address 5. It's all in the metadata. And the mapping from older to newer versions is done on the fly. So it can be handled in streaming data as well. So the incoming data then is put off heap, and the objects are created, populated, and linked. These are the 3 phases. It's not stack-based recursive linking, and it supports an arbitrary depth of an object graph. So the complexity isn't limited of the graph you're handling. And there's no code generated, no bytecode hacking, no replacement of instances with Praxis or any other monkey business. It's just a plain Java API doing low-level memory stuff and creating objects in the original state. So the 3 steps again. When the data is put off it, we do it so to not bother the garbage collector with on-heap data. Then objects are created by assigning memory addresses to object pointers. Then fields are populated by just writing data to this assigned address. And then the objects are linked afterwards, and the JVM then knows that objects are there and can be used. So there's no code which is executed, and it's the fastest possible way to deserialize data. And that's why the performance benefits come from. All right, so that's a bit of technical background. There are almost no limitations, of course. Almost meaning almost any object can be serialized. We had to blacklist some objects which cannot be deserialized when they have or when they bring external state, like a Java thread, or which is linked to a system resource or an open socket or input streams and stuff like that. These types are on the blacklist. But basically any object which is used in a business application, collections and poachers and whatever objects you're using can be serialized. So there are no requirements for classes, so you have no special interface. You don't have to implement Java.io serializable or any other interface. You don't have to extend from a superclass, and you don't need annotations as well. So you can use pure poachers, pure Java code without any special needs. So for separation of concerns, we have external handlers. So you can, but you don't have to put the code which customizes the transfer or the conversion from objects to byte and back, which is done by type handlers. They can be used externally or created in a different class and then registered at the serializer. And so you can write custom handlers, for example, for third-party library classes as well. So the depth, like mentioned, is not limited. And the class changes are covered through the legacy type mapping, which I talked before, where it's an unlimited amount of versions which can be handled because the engine registers kind of a type lineage with the different steps from version 1 to 2 to 3 to n. And so you're not limited in the class changes as well. That was a point we wanted to cover in order to get the storage engine done properly. Yeah. So, yeah, I can take the questions in between, of course. One was, so serialized classes are automatically loaded and land on the heap space. Yeah, of course. If you want to recreate objects, you have to put them on heap. That's where the object lives. Yeah. So if you put data off heap, the JVM doesn't recognize them as objects, and the garbage collector can't handle them. So, but you can use a white and black listing in our engine as well. Yeah. And it's a thing which every serialization framework has to tackle. Yeah. All right. So we did a performance comparison because it's a highly optimized native byte format, very similar to the JVM format on the heap. There's no big overhead regarding conversion. We don't have a needless overhead by string conversion for human readable data format, and tests showed that we can gain a big performance win out of that. All right. For recap, the benefits we achieved, it's easy to use. It's pure Java, has no external dependencies except a logging facade. There's no internal configuration needed, but you can use external handlers. You can use your classes as they are without adding interfaces, annotations, or whatever. Almost any object can be serialized. It fits seamlessly, of course, because of the aforementioned points to the Java object model. It's a high secure data transfer in Java, redundancy free, and of course we made it open source, and it's available in the Maven Central under these coordinates. And the source code is available on GitHub. I show the links later on. So let's look at some code here. It's easy to use. You just instantiate a byte-based serializer with a factory method. You can the serializer basically can use every transport or medium format as well. What we implemented is byte arrays and byte buffers, and the two methods you'll probably only use are serialize and deserialize, of course, and that's all a serializer does. It creates a transport format out of objects and recreates the objects out of it. And that's all you need to know basically about the serializer class in the first place. Of course, if you want to do some customization, it is like the storage as well, a interface-based architecture, so you can customize every single aspect of the engine and exchange stuff or tailor the framework to your needs. Mostly it's not needed in most cases, but if you have to, you can, and that's the important point. So let's say we want to write a custom type handler, meaning we want to customize how an object is converted into bytes and back. So we take control over the storing and loading procedure of a specific Java type. We can optimize performance and memory consumption for complex objects, and we can use, like mentioned, external configuration, unlike the Java serialization does. We have a given class called a time slot. Let's say this is we have sensor data coming in, and we have a huge amount of time data coming in, and we want to optimize the created byte format for this certain class because we can optimize or shrink the used memory and storage space down to a third or fourth, like we can see here. And if you use a class very heavily, it's probably worth the effort. So let's say Eclipse Serializer analyzes the type. We bring optimized type handlers for the most used types in a JDK, like the collection types or date, time, and so on. But every other type is handled by a generically generated type handler. It just analyzes the class layout, and it says we have a primitive data and we have object data. Primitive data is written directly into the object's byte stream, but object references create new records in the byte stream and then are referenced by this time slot record. And like we see here, we have the time slot itself and two date instances, meaning the engine creates three records. First is the time slot itself. It assigns an object ID and a type ID, and then comes the data. One meaning it's, for example, one is the slot number, and then we have two object IDs for the dates, which are written in new records. We got a different type ID, of course, and the data is just the timestamp inside the date, the Unix timestamp for this certain type, for example. So what we want to do, we want to inlay or embed the data of the dates directly into the record for the time slot, and therefore strip it down to a single record out of three. Because if you restore time monitoring data, we don't care about referential integrity. We just want to use the data. Of course, we could have used just longs in the time slot. Then a single record would have been created anyway. But we want to use a good Java API or use local data or whatever. Then it's mostly better to write custom type handlers and use proper types or date types for the inside your program. All right, so how can we achieve that? There are two ways to write type handlers. The first one is you can, if you own the source of the object, just add a static method to the type, which returns a type handler, and the engine will recognize this automatically and assign this type handler to the time slot class. It's done with factory methods. You just say, I want to create a binary type handler for a certain type. And we have field handlers for the field, and it's always the same game. We create primitive data out of it and assign the primitive data back to the field. All right, so that's one way to do it with the factory method, or we can use external handlers and register them in before we create the serializer instance. Let's say we want to create a type handler for a JDK class, like the buffered image. We want that the buffered image is encoded as a PNG file when it's serialized. So we extend a binary handler with a custom value. We have a lot of abstract clauses for that. For some cases, for array data or list data, and for single field data, you can just override the store method and call the store. The binary interface is basically the transport, the byte transport, which you write the binary data into, and you have a lot of methods like write store in, store long, and so on. And you can use store bytes and hand over a byte array, which is just an PNG encoded image in this case. All right, so these are the two methods how to customize a type handler or write a custom type handler. And the next one would be how to handle a legacy type mapping. Just a short information is you can take control over the migration from one object to another. The most common cases are covered by the engine itself. Primitive type conversion, for example, is covered. You don't have to write type converters for that. But if you have more complex conversions, like you want to split up a name into first and last name, you have to write a custom type handlers for that, because the engine doesn't know how you want to proceed for this. Yeah, it's described in detail, of course, in the documentation how to do that. And before we show some more code, these are the links. It's under the hood of the Eclipse Store project. That's the site, the Eclipse project site, and of course the GitHub repository. All right, so I have to share a different screen. Just a moment. So let's see. For a test, we have the person class in our serializer demo here. It's just a simple poacher with a name and a date of birth. For demo purposes, it should be fine. And it overrides equals and hash codes, so we can do an equality check after deserialization. So let's create person. Let's spawn pretty young guy. Let's say October 30th. Now we create our serializer instance. We can use the factory methods. We have our serializer based on byte arrays and two simple methods, of course. Serialize our person. We get bytes, and if you want to convert it back, we call deserialize, and we got our and we do a little check. If the serialization is correct, let's run it. And we see, of course, it's equal to the data before. So this method only works because we separate data and metadata. In this byte array you get is only consists only of data, no metadata. So this method only works if you serialize and deserialize objects with the same serializer instance in the same JVM, of course. If you want to send data to a different JVM, to a different machine, you have to tell the serializer which type he should handle. And this can be done with the serializer foundation type. The foundation is basically the configuration for this serializer, and it is used as a base for before the serializer is created. So we say foundation new, and in the foundation we can register entity types. Let's say the person, and then we create the serializer based on this foundation, and we can use the serializer on different machines. If I don't know which types may come in, then there's a different possibility. You can use a typed serializer, which sends the type information within the byte stream. So this is you have to be aware that the type information is transferred in the data. So you have to ensure a secure environment, of course. If you use if you transfer data between machines in a cloud in a controlled environment, you're good, or you're good to go. But if I wouldn't use type serialized data or type information in a meta information in a data stream on open endpoints, for example. So I would rely on whitelisting, which is fine for most endpoints because the data isn't too complex most of the time. All right. So a little preview for what's coming up. The serializer for now can handle bytes and binary, meaning byte buffers, which can live off-heap if you like. If you have to create data out of bigger object graphs or really huge object graphs, I would prefer the byte buffers, so you don't pollute the heap space. But for most use cases, byte arrays should be fine. And we are developing currently a stream-based serializer where you can hand over an input or an output stream, and the serializer writes the data directly over the wire or in a socket or whatever you're using, and the data won't live locally at all. All right, so I'm through with my code. If you have further questions, we have a bit time left. Yeah, one question. What about frameworks that need to implement serializable like Hibernate? Could we somehow replace serialization by Eclipse Serializer? Yeah, it depends on the framework, I guess. I don't know the internals of Hibernate too much. But a lot of frameworks like caching frameworks or even key value stores or data grids offer the possibility to inject custom serializers. And we tested it with Hazelcast, for example, or different caching frameworks, and it's working well. On the other side, if you have POJOs which implement serializable, it doesn't harm the Eclipse serializer, so it will take these classes fine. Yeah. Yeah. Can the framework detect classes that have been changed between serialization and deserialization? Let's say you have the sender has an older version and the receiver has a newer version of the classes, and that's detected by the serializer. If there is no manual mapping provided, it tries to create an automatic one. But just to go sure or to cover the complex cases, we suggest to always provide a mapping if you change your types. Yeah, and that's detected inside the stream. Yeah, and basically all cases can be covered. So if you add fields, rename them, even rename a class, so all refactorings can be covered by the type mapping. Yeah. Yep. You can provide mappings for different versions because the Eclipse Serializer meta format um, handles every change as a new type internally. So if you have a person and you add a name, the metadata sees it as a new type. And so you can have three or indefinite changes covered by this format. Yeah. So, and if you have, for example, version 1 in a data and a version 4 in the receiver side, the receiver will map from version to version, so no information gets lost. So it will do a mapping from version 1 to 2 to 3 and then to 4, and so you can uh, secure the data or make sure no data is lost. Yeah.